All right, guys, I think we can go ahead and get started. All right, so just as a reminder, I'm going to start introducing chemistry of dienes. Today we're going to discuss this idea of conjugation, what makes alkenes in conjugation with one another, what the result is that on the sort of reactivity of alkenes, and then we'll discuss a couple more reactions. We're going to go into a little bit more depth next week after the exam, so whatever that is, next Thursday, we'll go into a little bit more depth on this material. Wednesday, so this won't be on the exam. The stuff we talk about today won't be on the exam. We will revisit it next week. Tomorrow, or whatever, Wednesday, will be a review. And so come with questions. And I'll bring material, but I think generally you guys have specific things that you'd like me to go over, so we can do that. Wednesday. The next class, yeah. No, but again, you guys are responsible for Organic 1 material, so every reaction you learn in Organic 1, every mechanism you learn in Organic 1 is fair game. So, all right, so that's one of the reasons why I pulled back. All right, so let's get into dienes. Specifically when we talk about dienes, what we're referring to is, right, is two alkenes. By and large, when we're discussing these dienes, there's a few different ways that we can consider dienes, right? As I sort of have drawn, we can look at a couple different types of dienes. So here's a diene, which we'll discuss is conjugated, and I'll explain that in a moment. And this is also a diene, but it's not conjugated. So this one is generally called a 1,3 diene. This is a 1,4 diene, right? And it's just sort of the position. So 1, 2, 3, right? So the alkene starts here, the alkene starts there. You can even think of it as bonds: 1, 2, 3, 1, 2, 3, 4. Now, this idea of conjugation and this sort of term conjugation has been floated around this is something that actually comes up in one of the earlier chapters, and we float this term around on occasion. Some of the areas where we specifically refer to sort of conjugated systems that we've seen recently, we've sort of discussed this generally within the term of resonance, right? So if we think about a system like an ester, right, we generally talk about the stability of esters, for example, due to the fact that you can delocalize these sort of electrons right, so you can sort of delocalize those electrons right through that sort of pi system that is the carbonyl, right? And so, in essence, the lone pairs on the oxygen are what we would refer to as in conjugation with the carbonyl. You have to be able to draw resonance forms for this, right? And so, if we simply broke this up, so this is conjugated. To sort of draw an analogy, right? If we have an oxygen and there's, say, a skip in it, right? So if it's just a ketone that happens to have an ether over there, so right, so this is an isomer of this molecule. The lone pairs now have that CH2 in between, so it is not in conjugation with that carbonyl, right? You cannot, there is no resonance donation, right, into that other carbonyl. There's sort of that methylene in between that effectively blocks that sort of conjugation. In this case, I think it becomes a little bit easier to see it with lone pairs. In the case of alkenes, we can also draw resonance forms through alkenes as well. right? So the conjugated one that we've shown there, you can imagine a resonance form, right, where you can put those electrons, say for example, onto that carbon. Again, this is very minor, but right, we can imagine that resonance form, and now we can sort of see that in a way, the electrons within that can then be localized onto this carbon. And so, again, we could draw this in a single step as well, right? If we take this diene and we draw it in a single step, we can do that as well. All right, and the reason that we can do these is that there's effectively no sort of word that we want to put in there. There's no sort of stopgap in between. The electrons are able to flow from one set of orbitals freely to the other set of orbitals through this sort of conjugated system, right? If we were to do the same with this diene, right, the electrons would have that methylene in the way, right? And if we tried pushing them down there, then we'd effectively have a Texas carbon there, and we wouldn't be able to sort of do that. So this concept of conjugation at its core simply means, because we'll see it with lone pairs being in conjugation, with pi systems, but formally what it means is it's an ability of a molecule to have its electrons delocalized throughout a pi system, right? I think that's the best way to sort of think about it, is this ability to delocalize electrons throughout a pi system. So we've seen it with esters, carboxylic acids, and many of the resonance forms that we've seen in the past. And so in this diene chapter, we're going to discuss a little bit about chemistry that involves conjugated dienes, and then we'll talk about class of reactions later on that involves chemistry that doesn't have conjugated dienes, but instead has sort of unconjugated dienes. Okay? We'll start with sort of 1,3 dienes. So you know what I'll do? I'll use this as a good comparison. So we'll start with this 1,3 diene. Okay, and so just as a sort of a thought experiment, it makes sense to do this. There's going to be some difference in the same way that there's differences in the conjugation of these two. We can also see differences in both the stability of these as well as what we'll see as the reactivity of them. So again, your book discusses this in a little more depth, but as I've sort of stated in the past, in terms of esters, right, esters are often more stable than ketones because of this ability to delocalize the electrons throughout the system. So conjugation is a sort of favorable property. Again, I always think about this as the claustrophobic nature of electrons. If electrons can move, that makes the system a little bit happier. So electrons like to be able to move. The ability to spread out and delocalize throughout the pi system is something that's good. So that you can read in the book, it talks about different energetic differences and so forth. Again, as you may have learned by now, I'm sort of more interested in reactivity and mechanisms of these, which I think help explain a lot of these things. And there's different reactivity between these as well, right? And so if we start with simple reactions that we've seen in the past and ask ourselves to predict the chemistry that would take place, we can imagine both these scenarios reacting with HBr. Okay? And if I were to ask you guys to predict the product that might form, if, say, for example, we just had one equivalent, of HBr. In the case of the 1,4-diene, right, what's going to be the first step in the reaction between this alkene. So first of all, there's not the same. There's symmetry here, but that's really not the point that I'm trying to make. We'll get back to that in a second. But here, one of these alkenes, doesn't matter which one reacts, but one of them is going to react with HBr. When it attacks, where's the proton going to end up on? The less substituted, right? Why? Because the carbocation is going to end up on the more substituted. And then that bromine is simply going to add in and make a bond here, right? And so what we'll end up with is pretty much a clean reaction where we add HBr in sort of Markovnikov fashion across that alkene. Now, if we do the same thing with this 1,3-diene, we might get something a little bit sort of different, or something perhaps a little bit unanticipated. Okay? Now, if I ask the first step of reacting this with, say, for example, HBr, sort of first prediction might be which which alkene might the HBr go after? Let me sort of raise that question to you guys. If one of those alkenes was going to react with HBr, say I've got a blue one and a green one. You know, the green looks just like a yellow. But if we're going to react with the blue alkene, or if it was going to react with the green alkene, which one might you think it might react with? What's that?
Green.
Show of hands green. Show of hands blue. About 50-50. All right, somebody that says, turns out the answer is actually a little bit more ambiguous. The people that said green, what do you think the reason is? Someone. So you have a donating group. Yeah? Okay, so you've kind of thought ahead to an extent, yeah. So let's just go through both questions, right? Let's just go through both of them, right? So if we react with the green, we'll first react with the green, then we'll react with the blue, okay? Now, of these two sides, right, it's probably going to be on this, the proton's going to end up here, right? Hopefully you guys would all see that. Why? It's a resonance stabilization, right? Right, again, you can resonance stabilize here, so if you had your bromine attack, right, what we may be able to get, right, is this Br group here, right? Alternatively, we might imagine this reacting at the blue side. If that is the case, okay, we have a proton there, we have our carbocation there, right? And then we have resonance stabilization. Or sorry, and then, oh, sorry, we'll get back to that in a second. And then the bromine might attack. Right, and what we may end up with is this compound here. So in this case, we've basically drawn two products. Again, and I think that an argument could sort of be made for either one of these, right? I think that this idea that chemistry is always going to lead to one or is always going to lead to the other is kind of not true in a sense. I think, again, it's always more important that whatever your prediction is of which one it's going to go after, there might be some type of reason behind it. So if we just use what we're looking up on the board, right, which one of these alkenes, if either, would you expect would be more likely to form? Right? Let's look at those carbocations. Do you guys see any differences between those carbocations, just at face value? We'll look back at the resonance forms in a moment. But at face value, those two compounds. So I'm hearing the lower one. Why might that lower one be more stable? We'll get back to that resonance formula. So I'm just saying at face value, absent from resonance. I'm just trying to get you guys thinking here. Yeah. What's that? Why? Okay. So that's a common misperception of substituted carbocations, right? So I've heard that argument made. So the argument was this is more substituted on this side because there's two methylenes. But again, that misses the point of that's not what we mean when we say more substitution. These are both secondary carbocations. Yeah. Yeah, that's probably what I would anticipate here, right? It would probably go to the bottom one, right? When all things are considered equal, this one has a double bond left over that's more substituted, right? And so the thought might be that this double bond might be a more stable thermodynamic. So that would be a thermodynamic argument, and that's kind of where we're going to head to this, is sort of thermodynamic versus kinetic arguments, okay? Now again, every single reaction is reversible. So if we were to imagine this chemistry working, we might predict, right? Based upon those reasons, we might predict this. And there may be some reasons behind it, right? We may say because that double bond is going to be more stable at that point, and we'll get back to that in a minute. The area where chemistry, and I think one of the frustrating things about organic chemistry is that oftentimes the book will often try to oversimplify things, or you'll hear things that will try to oversimplify more challenging and more difficult and more ambiguous problems. Because another argument that you could make is that it might go to the top one, right? So you might predict this based upon stability, right? You might predict this one. Nobody did predict this one. But if I were to sort of look at it at face value, I might, in fact, predict the top one because that alkene is di-substituted. That means it's more electronically rich. That means it's a better nucleophile, right? And thus it might react. And so in this way, there's this sort of ambiguity that makes predicting reactions a little bit difficult. And that's why I'll just sort of make the point here that oftentimes your explanation, anytime you're going to predict things, is going to be much more important than necessarily getting what the answer necessarily is. And so I think a question that was asked like this, if you said right off the bat, the bottom question, the bottom answer, and you gave that explanation, I think that would be great. I think that would be fantastic. If you predicted the top product, and you said it's going to be because this double bond is more substituted, thus it's going to be more nucleophilic, I'd say, okay, that makes sense based upon the rules of chemistry. There's nothing wrong with the explanation from either standpoint. And in truth, in a chemistry lab, when we're running reactions, we often will assume that it'll do one thing and it'll do another. So it's much more important that you guys have some type of a basis for your argument within this sort of idea of fundamentals of chemistry, somehow explaining it even when there's some ambiguity to it. Okay? So simply by having that extra group in there, that's complicated this a little bit. And so to sort of simplify the question a little bit, I'm going to take a step back, and we're going to sort of eliminate these two possibilities for now. But what I'm going to talk about can extend to this if you guys are sort of thinking through problems. Okay, so I'm going to switch this up a little bit, and I'm going to sort of make it only just 1,3-diene by itself. Okay? Now, as we just said, when this reacts, now the first step that we have here, right, might be that you have this proton, that you have the proton end up on the less substituted carbon. You're then going to have the bromide come in and attack. And what you'll have is HBr. But the special thing about conjugated systems here, right, is we were just talking about sort of resonance stabilization of each of these, right? And so what we also have is this sort of resonance form, right? Where we can, in fact, push that electron over here. We'll get this carbocation, right? And then what can happen is the bromine can react, and we can get a completely different product. Okay, so we've effectively added a bromine. In this case, we've sort of added it 1, 2, right? In this case, we've sort of added it 1, 4. Now, of these two possible products that are forming, there are certain parameters that could, in fact, dictate what's going on here. And I think unlike the other one where there might be some ambiguity there, it's not to say there wouldn't be ambiguity in this one, but at least in terms of your book, I think it can sort of simplify it to an extent in which we could start to talk about competing factors of any reaction. So, namely this idea of thermodynamic control and kinetic control. We've discussed this a little bit in the past, right? Reactions that are kinetically controlled are generally the things that are going to form the quickest. The things that are thermodynamically controlled are those things that, if you let them equilibrate, is going to go to the lowest energy product. And sometimes the thermodynamic and kinetic product are the same, but in this case, this is an instance where they're not, right? And so, when we think about the addition of HBr to this system, right, the first thing that can happen, right, is that bromine can react with that carbocation, and right away you'll get to this compound here. Not allowing it to undergo this resonance stabilization, perhaps, would allow you to effectively get to this product, which would be the fastest one to form, right? And as it turns out, if you run this reaction at, say, for example, short periods of time, low temperatures, so short time, low temperatures, you might be able to get lucky and get this sort of addition that would take place simply by not allowing this sort of equilibration to take place. Okay? So you would attack it, and then right away it would sort of react with that carbocation. You would end up getting the kinetic product. If meanwhile you let this reaction run a little bit warmer temperatures, perhaps you let the reaction go a little bit longer. Again, every single reaction in this process is reversible. So what's going to happen is it's going to go to the most stable product. And for reasons that we just discussed earlier, this, well, maybe not this one. This compound here is, in fact, going to be the most stable product. Why was this one more stable than the other one that I drew? Why did I just... Yeah, because I drew it in the cis configuration. This is the trans configuration. So this is going to be... Sorry, I just based it on my previous drawing. So yeah, so that would be another intermediate in there, but that would lead to the cis, which is higher energy. So yeah, it would likely go to the trans. And so this would be what we would consider the thermodynamic product. Okay? And again, if you want to try to get a thermodynamic product in any reaction, if you know what the thermodynamic product is in the reaction, then at this point you can run it longer times, higher temperatures. Right, you might be able to get this other product. So the important point here to sort of recognize, I think the most important thing here is that, and this comes into play with the other one as well, is that there becomes this variability within dyene systems where you can begin to get multiple different reactivity. And when you do this chemistry and you're sort of predicting what types of products you might get from any given reactions, it's important that you sort of consider the factors that are at play and make a prediction that you would get a product based upon, you know, what we know about chemistry. So again, in this case, again, the more stable alkene would be the thermodynamic one. We can translate this forward to the previous problem that we saw and start looking at the overall products, and perhaps we can discuss that again next week, because I'm going to go basically everything that I talked about today, I'm going to go through a little bit more depth next Thursday. Okay, so this is the sort of general idea of thermodynamic control versus kinetic control. And we start to see it with dienes, and what allows dienes to do this is this ability to have this sort of resonance stabilization. Okay. All right. All right, so you can imagine a lot of chemistry that we've done to date. You know, if you want to do some similar chemistry like that with acid and water. Again, doing it with HBr, we've seen a lot of chemistry that's analogous to HBr. We've seen acid and water, we've seen acid and alcohols, HCl, perhaps bromine and methanol or something like that. But a lot of chemistry that we've seen with alkenes, you could sort of think about within that, and maybe we'll get a chance to do that at some point. But what I'm going to spend the next probably half hour discussing is a new reaction, one that I think is perhaps one of the most powerful reactions ever developed for organic chemists. It's certainly a new type of reaction that you guys haven't seen, but involves chemistry with dienes where you begin to have concerted processes and make multiple bonds, different stereocenters at the same time. And this involves a reaction called the Diels-Alder reaction. Okay? And so to introduce Diels-Alder, we're going to start by talking about the molecular orbital theory within diene systems. Okay? So, as we've sort of discussed, everything that we're drawing on the boards, every molecular structure that we draw is simply a representation of something that we can't really see with our own eyes, right? It's our interpretation of what's taking place, and what you can draw on the board and what we're actually seeing are likely entirely different. But theorists and whether it's experimental theorists or people use computational in combination with experimental theory eventually started to understand these dienes in a little bit more depth than simply this conjugated system that you could draw resonance forms through. And what they began to discuss this within is this idea of molecular orbital theory. Okay, and so the Diels-Alder reaction, which we'll see, is going to be a reaction between an alkene and a diene to get this. And it's worth it to sort of to explain this and understand how this chemistry works and how other chemistry that we'll discuss doesn't work. We have to sort of understand the molecular orbital theory behind it, okay? So here's your standard diene, right? And what happens when we have these conjugated systems is that the system doesn't necessarily represent two separate alkenes. They sort of combine together and create effectively a new orbital system, okay? And the way that we'll often begin to think about that is, again, it gets a little bit complicated in terms of nodes and all these other things, but the way that we start to think about this system is, again, there's sort of energetics between here, there's like wave functions that are involved. I'm going to give the sort of synthetic organic chemist way to sort of think about this answer that at least sort of allows us to sort of understand it. And so when we begin to start thinking about molecular orbital theory, we begin to think about how all these p orbitals are interacting with one another. Okay? And again, there's sort of wave functions involved in this system, but we have a series of p orbitals, and what we're really looking at is how those p orbitals are going to interact with one another. And it turns out there's different energetic states that sort of represent how these might be able to interact with one of them. In the lowest state, all of these orbitals, there's no nodes, all of these orbitals interact with one another, and effectively what you have is one big pi system, right? One big just overall pi system where each of these, both these orbitals sort of interact together, It's the lowest energy state. And so, and again, I'm not a quantum chemist, but what happens is when you start to fill these up, you begin to start putting electrons into these. And so you put a couple paired electrons into this system. There's 4 electrons total. And so 2 of those are going to end up in the lowest system. Again, I'm not entirely understanding of the sort of math and everything that goes behind why you do this, but as we'll sort of see, sort of understanding this overall process can then translate to understandings of a lot of other processes. So just bear with me. Okay? The second lowest energy, right, instead of there being no nodes, the second lowest energy would be one where effectively there's only one node, right? And so it's the second most overlap. So we're going to have these 2 guys overlapping over here. We'll have these 2 guys overlapping here. There'll be one node, right? And will effectively exist like 2 alkenes, right? So if in the bottom case, it's existing as one big 4-carbon pi system, in the second highest energy level, it's 2 pi systems, in essence. Okay? And again, we're going to stick a couple electrons into there. Okay? As we go up further, right, we'll go to 2 nodes. So when we do 2 nodes, now we only have sort of one smaller pi system, and what we have is sort of these other electrons, which are not necessarily in conjugation with one another. And then the last one, you're going to have nodes at every single point. So there's going to be, in fact, no overlapping of these electrons at all. Okay? And so the way that you end up doing this, and again, I'll sort of go into this and use this sort of model as a way to explain a lot of the chemistry, but the important thing to recognize is that there are these different energetic states that molecular orbital theory effectively allows us to consider. The lowest energy of them is the one where we effectively have no nodes, where it's just one big system, right? The second one would be the second highest, so it's just one node. You've effectively got 2 conjugated systems, and then sort of so on and so forth, okay? In the overall system of the pi system, we have 4 electrons, and again, you sort of fill it up. You always do these in terms of paired electrons, so you put the 2 down here, then you put the next 2 here. But then what happens is in these 2 higher energy systems, you actually don't have any electrons. And so the overall system, and this partly explains why it's sort of a more stabilized system, so the overall molecule and the overall electrons exist as sort of a hybrid of these 2 sort of states. Okay, so that's what sort of diene is. It's a sort of combination between this MO and this sort of MO here. Now, there's still an energetic. There's still energetics here, so this is lower than this one. And where we'll often look to chemistry and where we'll often refer to chemistry is this idea of the sort of frontier molecular orbital theory. So we look at where the chemistry is taking place. And so as we'll start talking about, anytime you get chemistry to take place, anytime you've got electrons in this system that are going to start doing chemistry, right, those electrons are going to want to be in the highest energy state, right? Does that make sense? So if you've got 4 electrons in the system and you're going to have some of them react, the higher energy of those is going to be the one that's going to be more likely to be how it reacts, right? These are where the electrons are. If you're going to have electrons react with it, this is the orbital that it's going to react with. Meanwhile, so this is what we will call the highest occupied molecular orbital. And so to abbreviate that as HOMO. Okay, so that's going to be what we refer to as the HOMO. And then this, did you guys college students? Lowest unoccupied, excuse me. So this is the LUMO. Okay, and so we're going to start talking about a lot of chemistry within these systems, and the chemistry will often be discussed within this idea of what does the orbital look like in the HOMO, and what does the orbital look like in the LUMO, right? Because if you're going to have electrons from this system attack, well, they're going to be the highest energy ones. They're going to come from the HOMO. If you're going to have, say, for example, electrons attack this, if you're going to want to dump electrons into this system, right? Well, they're not going to be able to attack this one because there's already electrons there. So where electrons would attack would then be the sort of lowest unoccupied molecular orbital. So this is just sort of a representation of what the electron orbitals look like, and then they end up having an effect on how the reactions actually take place, okay? And so we've got the sort of the HOMO and the LUMO. Okay? Now, this is the HOMO and LUMO of a diene system. In the case of an alkene, what we'll do together is we'll start to sort of discuss what the LUMO system looks like, HOMO-LUMO system looks like in an alkene, in a simple alkene, right? So if you only have one pi bond, right, this will still have some sort of parameters that you can sort of draw in this way, but it's not going to be quite as much, right? There's really only 2 electrons in the system. We only have the sort of possibility for one node, right? So in the same way here, right, we're going to have one where they're all going to be filled, or in this case, again, it's a smaller system, so we can't have more than that one node, right? We can't have 2 nodes because there's not room for 2 nodes. And again, the quantum chemistry is a little, I'm going to be honest, beyond me. But again, from this standpoint, in terms of this model that we have, right, we can now see that in the case of the diene, right, this is now the HOMO. And this other one is a LUMO, okay? So the way the molecular orbitals look within an alkene and where the sort of reactivity takes place is going to be in the system between the sort of HOMO, where this is going to be the HOMO and this is going to be the LUMO, okay? All right, so let's translate this to the Diels-Alder chemistry in terms of why Diels-Alder chemistry works, okay? Now again, what these all sort of represent are different energetic levels and again, wave functions and things that you can learn about in a quantum chemistry course if you would like. But in general, if we start thinking about the chemistry that's going to take place in this system, right? The chemistry is inevitably going to take place, it's not going to take place between the HOMO and the HOMO, right? What we're going to do is we're going to take the highest occupied molecular orbital of one, and we're going to react to the lowest unoccupied molecular orbital of the other. Again, the highest energy that has electrons, which makes sense, right, will react with the lowest energy one of the other one that doesn't have electrons, right? You want an area where there's availability of electrons, and you want the other one that has electrons, and they're in the highest state, right? So the lowest energy without electrons in one, the highest energy with electrons in the other. Okay, so when a Diels-Alder reaction takes place, one of the things that you'll notice, I'll just draw this a little bit differently, I'm just going to draw a curve to sort of show how this works. What we're going to do is we're going to take the sort of the HOMO here, and we're going to see something when I do this. Okay, so we're going to have that system there, okay? And then when we react this with the LUMO, okay, what you're going to notice is that at the points where those bonds are going to be formed, again, this is a high energy, this is the lowest energy process, give me a second more. This is the lowest energy process, right, when you have all the nodes in the same sort of energetic parameters. So does it make sense then that when a reaction is going to take place, right, it's going to be energetically favorable if you have the same type of system here, right, where on this one side, this lines up as the node on the top with the sort of alkene over here, right? So this node is going to line up with this one. It's going to be the same shaded area on the top. And this side over here is going to be the same sided area on the bottom. So they line up in terms of the sort of molecular orbitals. They end up having this match at the carbons in which they react. Does that make sense? Molecular orbital theory can be a little bit, take some time to digest. So I'll spend considerable time going over some examples that have this to at least go through repetition to get you guys thinking about it. Margot? Yeah. Okay, so this idea of the sort of nodes on the external part where the carbons interact with one another, you sort of want this matched system. Okay? Now, let's say, for example, so why is this important that we think about the molecular orbital theory within this? Okay, here's two double bonds reacting with one another. Okay? Here's two double bonds reacting with one another. If these are going to react with one another, right, what we'll have to do to sort of predict whether or not these can react, so these don't, and I'll explain it why. So what we'll do is we'll take the HOMO of one, and we'll take the LUMO of the other. Right, again, because it's the highest energy that has electrons in one orbital, the lowest occupied molecular orbital, the lowest one that doesn't. What you see is that one side matches up, but then the other side doesn't. Right? And so 2 + 2 reactions actually don't work thermally. Okay? Same thing with, say, sort of idea of 4 + 4, right? If we're going to try to do 4 + 4, that's not going to work either. Again, because if we sort of go through the system here, we take the HOMO of one, right? And we try to react it with the LUMO of the other. What we'll see is that one side matches, right? But the other side doesn't match. Okay, so there's this sort of special idea within this sort of frontier molecular orbital theory, or this ability of molecular orbitals to sort of create this concerted reaction where all these pi systems react with one another. They sort of need to have this relative symmetry, if you will. Right? This idea behind the sort of HOMO of one reacting with the LUMO of the other. Margot. This make us. Well, you can have this alkene react with this diene. It would be a Diels-Alder then. You would get a different product. You wouldn't get a cyclooctadiene. You wouldn't get the cyclooctadiene. You'd get a cyclohexene with an alkene hanging off. You know what I'm saying? Right. So if you try to do this, you wouldn't get that. What you would get is something like this. Right. So this would be. Right. So that would be. Hang off the other. Okay. All right, so there's a special symmetry within the molecular orbitals that allows Diels-Alder to take place. Okay. Now, when we start talking about chemistry of Diels-Alder reactions, as I've sort of drawn, this is sort of classical representation for Diels-Alder chemistry, but there's an electronic parameter as well. Again, we've just sort of shown it in its basest form. Okay, but when you run a Diels-Alder reaction, if you just simply take just 1,3-diene, 1,3-butadiene, and you take acetylene, and you react them together, it's going to be a rather sluggish process. You can get it to go, probably, but it's probably going to be fairly sluggish. So you generally don't see Diels-Alder chemistries run with just an aliphatic or just some. There's usually some type of an electronic match and mismatch, and what that leads to is sort of regiochemical control of the chemistry, right? So if you have a system that's, say, for example, a diene, this is going to be the sort of the classic normal electron demand Diels-Alder. So it's the HOMO of the diene, the LUMO of the alkene. And so quite often what you'll see in Diels-Alder chemistry is you'll have a system where you have some type of donating groups on the diene. So generally the dienes are electronically rich in some way. So again, we put that methoxy group there. That's going to add electronics into that system. Even just a methyl group, for example, will add sort of electron density into the system. Again, making it have a lot more electron density, have more electron character. Then it's going to be more willing to give up that electron character, right? And meanwhile, the LUMO, which is the unoccupied one, oftentimes what you'll do in this case is you'll have electron withdrawing on that one. So oftentimes you have an electron rich diene, and you'll have an electron poor, say, like acrylonitrile, right? So you'll have an electron poor right? And so this might make sense, right? If you want to soup up the electronics of one and make it a better nucleophile, if you can sort of think about the diene here being the nucleophile and the alkene here being the electrophile, if you add electron withdrawing groups to the electrophile, right, you're going to make it more electron poor, you're going to make it more likely to want to take on more electrons, right? Meanwhile, if you have think about your diene as being the nucleophile, right, so we can sort of think about that here. This is the nucleophile. We can think about the LUMO as the electrophile. Right? So if you make it more electrophilic, if you make it more likely to want electrons by adding electron withdrawing groups on it, then that's going to even be a better electron withdrawing group. Okay? So this is generally what you have in Diels-Alder chemistries. You have substitution on the alkene that's electron withdrawing. You have substitution on the diene that's electron donating. And more importantly, you end up having a regio selectivity that's involved here, okay? And so I'll just sort of explain some thoughts over here. So let's think about the two regiochemical outcomes that could form here, right? We could have and we'll get into stereoselectivity in a moment, right? But one thing that you can get, so we'll get back to stereoselectivity, that's a separate issue. First, I just want to talk about regioselectivity. So what you can do is you can have it react in this way, or alternatively, I can flip-flop this. Okay, so here's two different regioisomers, okay, they could form. And it turns out that one of the real nice things about Diels-Alder chemistry is that there's oftentimes very good regio control. And what you're going to need to be able to do is understand why the regiocontrol and why you get a specific regioisomer in this reaction. Okay? And the way that we can do that is by thinking about, we discussed this perhaps a little bit specifically when we talk about carbonyls reacting. We've talked about this a little bit when we talk about alpha-beta unsaturated esters. We think about this idea of where the sort of delta positive is, delta negative, right? You guys have seen these sort of delta positive, delta negatives, which effectively represent partial positive charge, partial negative charge, and where those might be in a given system. Okay? And so when you're thinking about Diels-Alder chemistry, one of the things that you want to consider is where is the delta positive of that diene? Where is the delta negative of that diene? And then the same thing, right, on the alkenes. All right, so let's think about that a little bit. Okay. Okay, so what I'm going to ask you guys to do is try to draw resonance forms of this molecule, where you put a positive charge here and a negative charge here, and then I want you to draw the resonance form with the vice versa. So what I want you to try to do is draw resonance forms that have a positive charge here, right? So let's look at the sort of, separate those charges. Let's look at a couple resonance forms. And what we'll do is try to identify which one of those two separations of charges looks more stable. And whichever one ends up looking a little bit more stable will ultimately be the one that has the delta minus delta positive. And then we'll do the same thing with the alkene as well. Okay, so think about resonance forms. Think about the resonance forms of this one first. So how do we do this? So I'll just use a couple different pieces of chalk. It's fairly simple, right? All we're going to do is look at two different resonance forms. Again, we saw this earlier when we were pushing the electron. Right? So when we draw the blue electrons, what we're going to end up with negative charge here, and a positive charge there. Okay, now let's go ahead and we can draw the green one, which is going to be the opposite. So there's the two resonance forms we're effectively looking at, where we have a negative charge at one of the carbons, where that carbon's going to sort of, where the negative charge, where you can imagine attacking, and then the positive charge being the one where it's effectively going to accept electrons. Okay? Of these two, does one seem to suggest a more stable, does one of these look like it would likely be more stable? The one on the top. Why? Right. So there's a couple factors, right? So first of all, the negative charge, right? Oftentimes we like to have the negative charges on the less substituted and the positive charge on the more substituted, right? And so that top one sort of represents that. The positive charge is on the more substituted carbon, the negative charge is on the less substituted. But in addition, this isn't only more substituted, but it has the resonance stabilization as well, right? So it has that resonance stabilization from the methoxy that effectively allows you to delocalize the electrons into there. Again, that makes it much more favorable. So, when we're looking at the structure here, the delta minus, again, the charge distribution is going to more accurately be represented by this resonance form. It's the same thing like when we start talking about carbonyls and showing why it attacks the carbon of the carbonyl, right? So negative charge there, positive charge there, that means that more likely represents what we're looking at here. And so we can think about this sort of negative charge, delta negative, being on the less substituted carbon, and the delta positive being on the more substituted carbon. Does that make sense? Okay. All right, let's do the same thing with acrylonitrile. Okay, so if we there are two different Okay, so now here we have the two resonance forms that you could draw, the two sort of separating the charges at the two carbons where you're going to have that chemistry take place. When we put a positive charge on one side and a negative charge on the other, and then vice versa from this. In this case, does one of them seem to be a more stable resonance form than the other? So I'm seeing some people point to the top. I think I heard a few people say bottom. Well, let's discuss, right? Let's discuss this. So the people that are saying the bottom, I'm willing to guess that you're assuming that it's because the negative charge is on the less substituted and the positive charge is on the more substituted. But there's one big difference here. Yeah. Yeah, what's that again? Yeah, exactly. Right. So this sino group, again, remember, it's electron withdrawing, right? And so what you've done by putting a positive charge here is, yes, it's more substituted, right? Right? It is more substituted. But the group that's substituted there is a highly electron withdrawing group. It's really going to be pulling the electrons away from there, right? Meanwhile, if you put a negative charge there, what can you do? You can draw a resonance form, right? So you can begin to draw the resonance form. So yeah, it's not, at least I'm glad that you guys had reasons for believing that this one was much more stable, but it turns out that this sort of resonance stabilization and electron withdrawing based destabilization of the carbocation that actually trumps this overall system. So it is this one on the top that's more stable. Right? And so again, what's going to look like, and this is similar to when we did, if you're confused about this, think about when you add 1,4 into a conjugated system, right? If you do a Michael addition, right? When you add that Michael, this is like a Michael acceptor, right? We are adding our electrons at this position because of that resonance stabilization. So there's this analogy here between where the delta plus is and where, say, for example, a Michael addition, where you're adding in terms of Michael addition. So if that's confusing, if you're trying to wrap your head around that, try to draw the parallel with Michael addition into conjugated systems, because this is a fantastic Michael acceptor. You can do Michael chemistry with that, so it's that same idea. So again, so over here, right, what we have is the delta minus there and the delta positive there. And so when we start to look at the relative regioselectivity of these systems, right, here's your delta positive, here's your delta negative, here's your delta negative, here's your delta positive, right? And you get this sort of matching up of charges, right? Where the negative charge is going to match up with the positive charge here, the positive charge is going to match up with the negative charge in the other instance. You can actually draw this. It's in such a way that you can, in fact, draw this, right? Like, if we draw it out as the full-blown charge systems, right? Right, we can start to see it like this, right? So where we have the lone pairs here attacking that carbocation here, and the lone pairs here attacking that carbocation there. So you guys see that? So maybe it's even easier to see it. So again, you should be able to make sense of it through the delta charges, through partial charges, but if you draw the full-blown charges, then you can maybe even see it even better, why this regioselectivity is the way that it works. So yeah, so if you run this reaction, right, what you're actually going to get is, you're going to get this regioselectivity. Okay, so there's a level of regioselectivity within Diels-Alder chemistry that can be predicted based upon the relative electronics. And again, given the fact that Diels-Alder chemistry is often done between an electronically rich diene and an electronically poor dienophile, you should be able to sort of do this. So you guys should all be able to, one of the things that you'll be expected to be able to do is to be able to look at a Diels-Alder reaction and predict the regiochemistry. And you should be able to do that using this sort of electronic arguments here. Okay. Now, in addition to the regioselectivity, okay, there's also a stereoselectivity and a diastereoselectivity within Diels-Alder chemistry. And this is where now we have to, this gets back to, I think, where seeing in 3 dimensions, there's a big struggle. So anticipate having to spend a bit of time understanding the diastereoselectivity. So I'm going to go through it today, and we'll go through it again next Thursday. But just give yourselves the time to practice understanding the diastereoselectivities, because I think it's rather uncomfortable at first, and it's going to take a level of comfort where you're just going to have to break through and really push yourselves to think about the diastereoselectivity. But I'll try to explain it to you in a way that at least it will hopefully make sense why it is the way it is. But the big challenge for you guys, a lot of you guys, is probably going to become actually drawing it, because it's going to be, again, that sort of three-dimensionality, seeing three-dimensionality in a two-dimensional space. Okay? All right. So when you have Diels-Alder chemistry, it's often best to think about this. We'll lock it. We'll use cyclopentadiene. And what we will do is we will imagine a reaction between cyclopentadiene and, let's say, silicon hydride. Okay? Or maleic anhydride, I forget the name of this. Anyways, this dienophile, okay? So we're going to imagine the chemistry between these two groups react with one another, okay? And again, what will probably become easy for you guys relatively early on is the ability to draw a Diels-Alder product without any diastereochemistry, without any stereochemistry. In this case, we don't have to worry about, I've made them both symmetric, simplified, so we don't have to worry about the regiochemical control, right? But the products are going to be so there's no stereochemistry drawn here, but I'm just sort of drawing it this way at first to show that there's effectively, it's a concerted process, but there's two stereocenters that we're really going to focus on. It's going to be the ones in sort of green, which are effectively going to be the same, and then the ones in sort of blue. Okay? Now, how we want to draw this, what I will do is I will actually focus on the protons here. Again, it's not I'm not drawing it enantioselective process. So let's imagine these protons are going back. And these protons are coming forward. So you guys know that when you have those big circles, that's a proton coming forward. I don't know if you guys have seen that in the past. You know what? I'm not going to do that. No reason to do that. I'll just draw. Okay, so those could either those could be the same, or these could be going back as well. Okay, now, oftentimes when we're looking at molecules in 3 dimensions, the big challenge right off the bat becomes actually seeing what that molecule looks like in 3 dimensions, being able to visualize it, being able to draw it, and so forth, okay? And so what you have to go back to the drawing boards, again, going back to like chair conformations and drawing molecules in 3 dimensions, I'm really going to push you guys, and this is where it's going to be important now, to start thinking about molecules in 3 dimensions again, and try to draw them, so it takes a level of artistic ability, okay? So there's the molecule, okay? And in this case, what we have, protons are going down, right? And if we have the protons here going up, we have that molecule there, right? So this, if you sort of folded it up, right, you'd see that this is effectively coming towards you. You try to fold this up, you'd see that these protons are coming up, that proton is going down, okay? So that's perhaps something that needs to be worked on, okay? And I recognize that. So I'm pushing you, I just really want to urge you guys to really practice drawing these molecules in 3 dimensions. Meanwhile, on the other side, right, this other molecule, they're going to be going down. These guys are not going to be going down. Okay? That's the proton going down. Okay? So effectively what you have is this cage system where on the one hand you have the molecule up near the methylene group, and on the other hand you have the system where it's down near the alkene. Okay? Now, there's names for these two products, and generally what happens is the group that's effectively closer to the alkene, okay, is the endo product. Okay, so that's going to be the one that's closer when that group that's attaching is closer, and I'll explain why, and perhaps why it's a little bit easier, why this actually happens, while there's selectivity for the end. In the other case, you have the product where the group is up near the methylene. Okay. Now, if I were to ask you guys, among these two products, which one you might think is the thermodynamically stable? I'm seeing somebody go, the one on the right. Why? Yeah, I mean, as I've drawn, it's probably not the greatest, but this is closer to the smaller group, right? This has methylene down there. It's actually, in this case, it's not the biggest of difference. But yeah, by a slight margin, this one is a little bit higher energy. Yet, when a Diels-Alder reaction takes place, very often you end up getting the endo, or the kinetically controlled product. Okay, so in many cases, the endo process will sort of arise. So in the last 5 minutes, I'm going to try to sort of explain this to you guys in terms of why this is the case, get you guys thinking a little bit about this, and then we'll go through this a little bit more in detail and in depth next Thursday. Okay? All right, so when these two molecules are reacting with one another, again, this is where the artistic ability comes into play. I actually had an art minor in college. I don't know if there's a connection there, but I wasn't very good at drawing stuff, but so what happens is if we can try to draw this right on its all right, so let me do my best here. Okay. I'll draw some blue just so you can see it behind it, okay? All right, so you guys see I'm sort of trying to draw this as if we're looking down the bond. Okay, so this is the diene. It's reacting, this carbon-carbon is going to be reacting with that carbon-carbon. Does everybody see that? So I'm trying to draw it in a way where this alkene is now coming at this alkene and this diene are sort of reacting with one another. I'm trying to show it from the top face. Okay? All right? This is the product, again, the alkene, this methylene group here, being on the same side as that group there. This is the molecule that's going to lead to the endo transition state. So this is the okay? Now, what you notice about in this system is, again, we've been talking about this idea behind molecular orbitals and how there's a sort of stabilizing factor of orbitals interacting with other orbitals, and so on and so forth. And the idea behind endoselectivity is that, by and large, when you have a reaction, right, oftentimes these groups on the dienophile have pi systems within themselves, right? So, again, we saw it with the cyano group, right? That cyano has p orbitals in it, right? There's those p orbitals. And in this case, we have, in addition to the p orbitals, right? In addition to the p orbitals with the alkene, right? What we also have is orbitals on the carbonyls. Okay? And so what happens is, when you're doing this Diels-Alder reaction between those two, you have an orbital-orbital interaction. Wow, that's horribly drawn. Okay, I'll go through this again. I'm going to try my best to salvage this horrible drawing, and then I'll try to do a better job of drawing it on Thursday. But what you see here is that there's orbitals that are in fairly close proximity, and maybe I'll bring a model next time too. What you see here is that there's an orbital here that's not involved in making the bonds. Okay? But when it's in the endo transition state, it's brought in very close proximity to the orbitals here that are also, they're involved in that process, but they're not the ones that are making bonds. Okay, so this is an orbital that's certainly involved in the chemistry, but that's not where the carbon-carbon bond's being formed, right? The carbon-carbon bond is here. But right adjacent to that, you have an orbital here, right? You have orbitals here, right? And it turns out that there's this orbital-orbital interaction that sort of stabilizes the transition state and actually makes the energy state, the transition state, to make these products go more smoothly. So it effectively lowers the energy transition state to the endo product, thus arising with the endo product. So I'll bring a model next week. I thought I'd be able to do a better job of drawing that. But anyways, with that, bring questions next week, or not next week, sorry, on Wednesday, and I will answer them.